All right, yeah. Go to the Falsifiability. I just uploaded the real quick.
Do you know if there's a way to like actually download?
Yeah, there's a little button that says, so if you click on it, there's a little button that should show up on the game that says no. I'll check on the handout. I just uploaded it. I didn't double check. Yeah. All right. Let's get started, everybody. So we're taking a bit of a turn in terms of the material that we're covering this week. It's going to be about the philosophy of science. There are a lot of readings that I really liked for this unit. I'm only assigning 2 of them, and they are a little bit long and dense, but I think they're valuable. For today, I mean, you may or may not have read this chapter by Zoltan Dienes. I recommend it. I think it's pretty clear. And I especially recommend reading it before you get to the Neal paper. The paper by Neal, I think, is fantastic. Neal, in general, is one of my favorite researchers. He's just extremely insightful. But he tends to write using a pretty dense style. So I think having the background of the Bloom's chapter might help provide some scaffolding for the paper by Neal. We're going to cover content described by Neal on Wednesday. There's a little bit today that is relevant to the Neal paper, but mostly it's going to be on Wednesday. So anyway, that's the order that I recommend. And if you're interested in these topics, I also posted a bunch of other readings that I do not expect you to have read, but that you might find interesting or useful. So, like I said, we're taking a bit of a turn from the last unit. In general, there's kind of this divide between statistics and sort of like scientific philosophy of science, conceptual kinds of questions. So this is a figure from one of Neal's papers. It's one that is posted on Blackboard, but it's not assigned. Neal makes this distinction between the theories that you test, how they're instantiated as statistical hypotheses, so like what you consider your null and alternative hypotheses, and the observations that you gather. And he argues that how you get observations translated to test statistical hypotheses that's like a lot of what you learn in a statistics class like this one. So everything that we've covered in terms of the general linear model and null hypothesis significance testing is sort of on this side of this figure. You can often think of statistical concepts using some of your like scientific and other sorts of knowledge as some background knowledge. But really, this is like one side of the chain of inference that you need to travel in order to, come up with scientific ideas. The stuff that we're going to be talking about today is more on this side. We've actually talked about concepts that might fall more on this side of the figure. So we had that whole unit last semester about different types of validity, like external validity, construct validity, reliability. Those concepts are more on this side. We also have that whole unit on causal inference. So when can you make causal claims and when might they not be justified and what sorts of assumptions are required to make causal claims. That's also something that I put on this side of the equation. Finally, we had that unit on like reproducibility and meta-science that I put over there as well as the things that we're talking about today. A lot of these concepts sort of bleed into each other. There are some relationships and some distinctions too. So we've been on the side of the figure. That's where we're going to be today and Wednesday. When you're thinking about philosophy of science, the kinds of questions that you're typically asking are things like, what makes something science anyway? So there's this question called the demarcation question. Demarcation means, what is that order that separates things that we think of as scientific from things that aren't, that are, you sometimes hear the term pseudoscience, or basically non-science. Metaphysics is another term that I think the Dean's chapter uses. Another question that you could ask is, how can you tell whether science is good or not? So among the stuff that's called science, there are usually better ways of doing science and worse ways of doing science. So what are the principles that we can use to determine whether something is good or bad science? And the last question is, usually when we think about science, one thing that we want out of science is that it progresses in some way. We'll talk about what that means in a bit, but there's often this idea that over time, science becomes better. There's some amount of progress, or at least there should be. So how do we ensure that science actually progresses in that way, and how can we tell if progress is happening or if it's not? So I'd argue that these are questions, even though philosophy is often abstract and presented as separate from a lot of stuff, and often it is, frankly. But these are questions that a lot of scientists are pretty interested in. How do you know if you're doing science? How do you know if it's good? How can you make sure that progress happens? So I'm going to touch back on each of these questions later in the lecture. I'm going to fill in some possible answers. The answers that I'll provide are meant to be the answers. They're just the answers that some people think are reasonable. So you can think for yourself, like, what do you think about the answers that we'll talk about today? And if you want to think more about, like, what makes science good and that sort of thing, one of the supplemental chapters by Dean's goes through a couple other perspectives on science besides the one that I'm going to be focusing most on today. So, one of the central concerns of science is making inferences. That's a term that's come up when I talk about statistics. So the statistical kind of inference that you often want to make is from some data that you have to some idealized hypothetical quantity that's out there in the world. So what is the population mean on the depression score among college students, for example? The kinds of inference that are relevant to science are more from the whatever statistical hypothesis you come up with to some sort of scientific theory. And one of the principal tools of inference is logic. So you may have seen problems like this. This is one style of deductive logic. The idea is that you start from a general principle and a statement that you take as true. So all P's are Q's. I'll give specific examples in just a bit. You observe a P, therefore you conclude that it's a Q. This form of logic, this form of deductive logic, is called a syllogism. It's one form of deductive logic. The bigger idea behind deductive logic is you're starting from the general principle and then applying that principle to a specific case. So I was really excited today that I got to talk about snakes. I don't think I talked about that much last semester, but I freaking love snakes. So I've got some examples up here. This is a type of viper. It's a snake. This is called a hognose snake. It's playing dead. They're known for being drama queens, and the snake is actually alive, although it looks like it's not. And This is my pet snake. His name is Smog, after the dragon from the Hobbit. So all of these are snakes, even though they look kind of different. Given the information that they're snakes, given the information that all snakes are reptiles, one syllogistic conclusion, deductive conclusion that you could draw, that's a perfectly reasonable one to draw, is that these snakes are reptiles. So we're applying the rule that you're given up front, that you're assuming to be true, and that is a logically sound inference. So there's a problem with applying this sort of deductive syllogistic logic to science, in that we're usually interested in finding out what the rules are. So we don't have the rules to begin with. That's our task, is actually to try to figure out some general principles that apply all the time, or at the very least, we want to be able to identify the cases when they don't apply. So we're after those general principles. They're not taken as a given. So it doesn't seem like maybe this kind of syllogistic logic applies sometimes in science, certainly not all the time. So that seems like an issue. So something that you could do to try to generate these principles is you might do something like this. You have a bunch of observations. You look at some common themes or some common aspects of those observations, and you basically generalize those common themes to some grander principle. So the inference is going from a bunch of observations that you have to a general principle. It's going in a different direction. So I'll give you a more specific example of what this looks like. Let's say it's clear from the picture, and I happen to know about this kind of viper, that this viper lives on land. It's one aspect of this viper. Hognose snakes also live on land. And Smog lives with me, so I also know that he lives on land. So if I'm applying this idea of looking at specific aspects of my observations and drawing the general principle, one principle or rule that I could infer from this case is all snakes are land-dwelling. Let me pause here. Do any of you see something, an issue with this kind of logic?
You're relying on observations in the case.
Right. And what's the problem with not being able to see everything?
Your rule messed up. That's what I'm saying.
This is a green anaconda. Anacondas that live in the Amazon. They spend the vast majority of their time in the river. There's also a kind of snake called a crate that lives exclusively in the ocean. So the moment I see an observation like this that works counter to the principle that I inferred, the principle is out the window. It's refuted. It's falsified. It turns out that this style of logic just doesn't work, because the moment I see an observation that runs counter to the principle is refuted. There's never a case when I'm gathering these new observations where I can be certain that the general rule will hold. Let me emphasize that again. Logically, there's never a point when I'm looking at these observations when I can say that the general rule will hold. No. That seems like a pretty big problem if, one of the things we might be interested in science is making inferences about these general principles. This style of logic is called inductive logic. You observe two things together, bunch of times, P and Q, P and Q, P and Q. So the snake is land dwelling, the snake is land dwelling, the snake is land dwelling. And you draw a conclusion like all Q's are Q's. The problem, once again, is that the general conclusion that you might be interested in drawing, you want to know whether that general conclusion is true. That's not something you can ever do, no matter how many observations you have. This problem has a specific name. It's called the problem of induction. And it's a particularly tricky problem with something like science, where you want these general principles, but you don't have them. You're not given those general principles, but that's something that you're interested in learning about. And actually, a fair amount of the philosophy of science is thinking about this problem of induction. How can we cope with this problem that, logically at least, this kind of inductive leap from specific cases to general principles is not valid. It's not logically guaranteed. It also seems like, we can only work with the tools that we have, right? If we're not given a set of premises that we know are true, that we can use to derive other things in that sort of deductive way. If that's not something that we can do, it seems like we want to be able to use something about the observations that we have to at least come close to these general principles. One answer to this problem, or potential answer anyway, and for most of this lecture, I'm going to be focusing on one person's work, sort of drawing on other people's work too. His name is Popper, very famous philosopher of science, very influential in science. But I just want to put that out there, that there are many other people who have written many other things about the philosophy of science. What Karl Popper suggested is that we use this interesting idea that if you see one counterexample to a principle, to a general principle, to our advantage. So we're flipping something that seems like it's a really difficult thing, it makes our lives difficult, into something that actually can work for us. So to be a little bit more specific, we're using the fact that if we see some sort of observation that runs counter to a theory or some sort of general principle that we're interested in, we're using the fact that this can serve as a powerful refutation of that principle as something that can work for us. It might be a little bit hard to figure out what that looks like, so I'll get a little bit more specific in a bit. Basic idea that I want you to get here is that we're using this kind of tricky thing of counterexamples, contrary evidence, as something that can advance science rather than stymie it. And it actually turns out that there's a type of deductive logic that makes this idea of refutation, that puts it on logically sound ground. So the style of deductive logic goes like this. You're still given something like all P's are Q's. And you observe a P that is not a Q. So what we know right now is that something about the rule, that the thing at the end, is actually falsified. And if we observe a P that is not a Q, we are justified in saying that P must not be true. So to put this in the context of the snake example, this is exactly what we did here. Our principle is all snakes are landfalling. We observe a snake that is not, so we know that not all snakes are landfalling. This is a logically justified type of inference. And there's a specific name for this. It's called the principle of modus tollens. I actually don't know what modus tollens means, some Latin name. You can think of this as the principle of refutation. You have a rule, you observe an instance where the conclusion that you want to draw is false. So you know that the premise is wrong.
Just a curiosity question. The three dots, what is that called?
Oh, that is a symbol for therefore. So that's the inference that we're making. So the way this works is you have a couple different premises given information. And then the three dots stands for therefore. That's the conclusion that you're drawing on the basis of the given information. So for example, you're given the rule, all snakes are landfalling. You're also given an observation of a snake that is not landfalling. Then the inference that's justified from that conclusion is that not all snakes are landfalling. So the strategy that we're going to take still involves some, like, you get some observations and you think about general principles that could hold for those observations. So you still might be doing some induction. You might be looking out there in the world, describing the world, and then thinking through what general principles might hold given your observations. So that's still stuff that you're doing, even noticing that there will never be the case that those general principles that you infer are going to hold for all time. That's just not guaranteed. But what you're doing is you're adding some extra steps to this process of induction or generating general principles from the specific cases. So one thing that you're doing is you try to actively think about what evidence that you might gather that would threaten the general principle. So you're actively thinking about, okay, given this principle that I'm interested in, all snakes are land-dwelling, where could I look to find examples of snakes that are not land-dwelling? If you have a specific theory about the effects of a drug on depression, and you think it'll act because of some neurotransmitters, this step involves actively thinking about what evidence you could gather that could falsify that idea that this drug has an effect on depression through some neurotransmitter. So you're thinking about the evidence that would refute or be inconsistent with the theory. And you're doing this proactively. The next step is that you go out and try your damnedest to find those observations. So you're trying to kill off the theory. You're trying to prove yourself wrong. So you think about ways that your theory might be refuted or falsified, then you go out and try to gather that evidence. When you go out to try to gather that evidence or those observations, two things could happen. So the first thing that could happen is that you actually find those observations. If that is the case, then by that principle of modus tollens, you know that the thing that you started with, that general rule, your theory, must be wrong. That's guaranteed by modus tollens. If you don't find those observations, despite your best efforts, you're not able to refute your theory. So you don't exactly find out that your theory is true. I mean, like I said, that's not something that you could ever find out. That's one of the problems with inductive reasoning. But something similar to truth might happen to that theory. So over time, if you've done your damnedest to refute your theory, you might increase your confidence in it. It gains sort of a quality that's a little bit like truth, even though it's not quite truth. So this seems like it could be a working model of science. We generate some principles using whatever tools are at your disposal. That could be looking at the world, drawing on other people's theories, deriving possible general rules through induction. Doesn't really matter how, but you try to generate those theories, those general principles. You think about ways that the theories or principles would be proven wrong. You go out and try to gather that evidence, and you either refute your theory and revise it in some way, or the theory survives refutation and it gains this sort of truth-like quality, even though it's not quite true. Does that idea make sense? So, that's all well and good, but things get a little bit more complicated when you get down into the details. And, people like Popper or some of the philosophers of science who came after him, like Henry Lakatos or Paul Neal, I'm going to ask you to read. A lot of these people were motivated by the idea of trying to work out these complications. And this is an area where, as with all of this, there's areas for reasonable disagreement. So I'll go through some of the complications and also be clear when I'm making statements that I think are true. You don't have to take those as a given. Like I said, this is an area where there's one can have reasonable disagreements. So one thing that has to go right, that could go wrong, is in this process of figuring out what observations could refute the theory. So not all statements that you make even have observations that can refute them. So to get a sense of what this looks like, this is a mathematical example of this idea that we covered last semester. Last semester, I presented this idea that as you add in extra parameters into a linear model, as you add in extra things that are to be estimated from the data, eventually you reach a point where your model perfectly fits your data. So specifically, if you have 20 data points, you fit a model with 19 parameters, that model will perfectly fit your data. This is a principle that also applies in logic. As you add in extra premises, eventually you reach a point where your model can explain anything. And if it can explain anything, it can never be proven wrong. You don't reach that point where you gain confidence in it because it survived refutation. Model that explains anything is not a very useful model. It explains nothing. Last semester, this idea that eventually you reach a point where your model perfectly fits your data, I call that overfitting. There's a point at which you're making your model way too complicated and it's not useful. Here's another example of that general principle. In logic, if you're creating scientific theory or evaluating a scientific theory, you can't think of a way that that theory could be refuted. You can't think of evidence that would be contrary to the theory. It's a sign that might not be a very good theory, at least according to Karl Popper.
Did you just say that you can't find evidence to refute the theory?
Yeah, if you're unable to, so this is in principle, right? if in principle, just if you're thinking about things that you could do out there in the world, if you can't think of a way to find evidence that runs contrary to the theory, it's not a very good theory. If on the other hand, maybe you're like surveying the literature and you just can't find a study that is inconsistent with the theory, well, that could be because that theory has people try to refute it, but it's been worn out. Or maybe it's because not many people have bothered to test it, but in principle, it would be possible to find evidence that runs contrary to the theory. So what I'm talking about here is being able to refute the theory in principle. Can you think of a study that could possibly produce evidence that would run contrary to the theory? Or can you think of a pattern of data that, in principle, would run contrary to the theory? That's the kind of question that you're asking. Like I said, sometimes that's not possible. So this is a good question to ask yourself if you're trying to evaluate whether a theory is good. Is it, in principle, possible to find contrary evidence? What study could I conduct that would put the theory at risk of refutation? So this idea of being able, at least in principle, to find evidence that runs contrary to the theory is called falsifiability. A theory is falsifiable if it's possible, at least in principle, to conduct some sort of study to get some observations that put the theory at risk of refutation. This is a very important idea. So I framed this whole lecture around these three questions. We've actually found an answer to one of these questions, the first one. One way to distinguish science from non-science is that science is falsifiable. In principle, at least, if a theory is scientific, that means that it can be put at risk of refutation, it can be proven false. So Karl Popper's, one way of talking about it is that it's the demarcation criteria. It's the thing that you look at to tell if something is science or non-science. Karl Popper's demarcation criteria is falsifiability. If you want to know if something is science, if you want to know if a field is science, ask that question, is it possible to falsify the theories that they're working with? So Karl Popper would argue that one reason that, say, studies of ESP are not scientific is that it's not possible to show that ESP doesn't exist, at least with the way that many ESP studies are conducted.
It's not possible to show that ESP does exist?
Doesn't.
Does not.
Yeah.
What is ESP?
Extrasensory perception, the ability to see into the future. There's this interesting, like many studies of the ability of people to see into the future, and some would argue anyway that one reason that these studies just sort of stick around is that the way the studies are conducted is not scientific. There's no possible way for the studies to get the answer that ESP does not exist. We saw one of these studies last semester because it was published in the most prestigious journal in the Journal of Personality and Social Psychology. So it was by a very famous social psychologist named Charles Down. Just to go back to the idea, one of the reasons that was so threatening to people like me who are doing social psychology is that it seems to suggest that the way we're doing social psychology is not scientific. It's not good. Anyway, this is a very important question to ask yourself. Is this theory falsifiable, at least in principle? One other important idea is that there are degrees of falsifiability. Some ways of constructing theories leave more room for refutation. To give you a sense of what this looks like, consider the following theory. Let's just say that we're correlating some variable with another variable. Let's say drinking and depression. I've created a theory that predicts that there will be a correlation between drinking and depression. But all I'm willing to say about this theory is that the correlation will be non-zero. So this red line right here are the range of patterns of data that refute the theory. The only pattern that refutes this theory is a correlation of exactly zero. And notice there's a lot of space over here where I could find other patterns of correlations, any one of which is consistent with the theory. So this particular theory that's just predicting non-zero correlation is not very falsifiable. It is falsifiable, but it's very hard to, because the theory explains, it purports to explain so much. So even though like having this restricted range of patterns of data that could falsify your theory might seem like a good thing, you know, it seems like we ought to prefer theories that are hard to falsify. Actually, according to Popper, it's exactly the reverse. If a theory puts such severe limits on what patterns of data falsify it, that's not a theory that actually is providing a powerful explanation for everything. It can't be refuted. It can't go through this process of being put at risk of refutation, but surviving. One style of theory that is slightly better is a directional prediction. So let's say my theory says that there ought to be a positive correlation between drinking and depression. Well, now my theory is excluding a larger number of patterns of data, but there's still a lot of patterns that it permits. There's a lot of space on this graph that's acceptable. So this is a little bit better, but still not super falsifiable. It's better. Let's say, in contrast, that I'm able to, using whatever tools I have at my disposal, say that the correlation between drinking and depression is going to be between 0.2 and 0.3. Notice how this excludes a ton of other possible correlations. There's a lot of space on this graph that is in color that is out of bounds from this theory. So the reason that this is, or can be considered a nice feature of theories, is that if I conduct study after study where I'm putting this theory at risk of refutation, but in study after study, I find that correlation is between 0.2 and 0.3, that's pretty dang impressive. That might boost my confidence that there's something close to truth about this theory. So that's the idea behind falsifiability. Another way of making theories more falsifiable is to say that they're about multiple domains. So not just drinking and depression, but let's say that I also say that my theory holds with drug use generally. So that's more domains where I put my theory at risk of refutation. It's another way of increasing a theory's falsifiability. So the general idea here is that you increase the range of values that put your theory at risk of refutation and it manages to survive after test after test. That probably ought to increase your confidence that this theory is good. This quality of like not being quite true because we can never guarantee that a theory is true. But gaining a quality that's kind of like truth, that's sometimes called verisimilitude. That's a fancy way of saying truth-likeness. Just want you to know that that's a term out there. Paul Miller uses it. I think it also goes up in the Dean's textbook. It's not quite truth, but it gains a quality that it's kind of like truth. So another general idea that you ought to get from this discussion is that we ought to prefer theories that are more falsifiable. We can't even work with theories that aren't falsifiable. We can't call those science. You know, it might be worth dealing with those ideas that are not falsifiable, but they're not science. And even stronger is this idea that there's a range of degrees to which theory can be falsifiable, and we should generally prefer theories that are more falsifiable, all other things being equal. There are other reasons you might like theories. This is one of them. So we've learned a couple other things that answer the second question. One thing that distinguishes science that is good from science that is bad is that good science generally makes predictions that are easier to refute. There's a greater range of values that could be considered inconsistent with the prediction. Another idea about how you can tell a theory is good is if it survives repeated attempts at refutation. If someone has done a study where if the theory isn't true, there's a lot of different stuff that could make it, that could allow you to see that. But despite those like very severe tests where you're only a narrow range of predictions are consistent with the theory, it survived those tests. And that idea of surviving repeated tests is called verisimilitude. The theory gains a quality that acts a little bit like truth, even though you can't ever be sure that it is true. Okay, so that's that first thing that has to go right. You have to be able to go through this process of figuring out the types of observations that could even in principle put the theory at risk of refutation. The second idea concerns what counts as an observation that is relevant to the theory. This might be a little bit hard to wrap your head around, but to give you a sense of what this looks like, to go back to the snake example, when I notice that these different snakes all are land dwelling, I'm paying attention to one aspect of the snakes and implicitly ignoring other aspects of the snakes. So I could have, for example, focused on the fact that they all have forked tongues, or they're all scaled, or they're all long. There's a lot of different qualities of these observations, these snakes, that I could choose to focus on. And if I have a theory that focuses on, the fact that snakes are land dwellers, that's highlighting that land dwellingness aspect of the snakes and de-emphasizing those other aspects that could be relevant to other theories. So that's one way to think about how certain observations, certain pieces of data are going to be relevant to theories, but others are going to be considered as not relevant. We've also talked about another manifestation of this idea when we talked about construct validity last semester. So construct validity is that idea that there are certain things that you can do with a measure, a way of requiring observations that make it good or not good. The whole general idea here is, when you're thinking about construct validity, is are you measuring the thing that you want to measure? And so there are certain ways of demonstrating that. We look for predictive validity, convergent discriminant validity. To give you a concrete example, let's say that you want to measure temperature, and one way of measuring temperature might be looking at the expansion of mercury. That's how a lot of thermometers work. That's not an obvious way of measuring temperature, but you might have other evidence that you know relates the expansion of mercury to temperature. So questions about construct validity are ways of figuring out whether certain observations are relevant to your theory. If you've got a theory about temperature, one way that you might know that the expansion of mercury is related to temperature is that you've got this evidence that shows that it's relevant to the thing that you're interested in. If you question the construct validity of some sort of measure, one way of understanding the question that you're asking is this measure even relevant to the theory that I'm interested in? Now, it's always a question that you can ask, in good faith or in bad faith, is, does this measure have construct validity? Is it relevant to the thing that I want to know about? Does this even qualify as an observation that I should take as informative about my theory? And this is something that people disagree about all the time. So if you have some study that purports to gather evidence that's inconsistent with your theory, you can ask, well, do your measures have good construct validity? Are you sure that you're measuring drinking if your theory is about drinking? Or are you measuring people's reports about drinking, which can be inflated by people wanting to look cool because they're working with college students? That's a question about whether this observation is relevant to your theory. That's this problem that people have to agree about what counts as relevant to even accept something as a potential interpretation. So the larger principle at work here is that you often need theory to even make that determination of whether some sort of observation is relevant to your theory. I mean, like a theory of measurement, basically, that suggests that this observation is relevant to this other theory that you want to test, that you might be more interested in. This idea that you have to make this judgment that often involves some other theory about whether a measure or observation is relevant to something that you're interested in. That's often called the impregnation of observation theory. Impregnation here means that the observation doesn't even have any real meaning in the absence of the theory. It's sort of shot through with theory. And that's the thing that makes it potentially refuting or not. Without that, how would you even know that the expansion of mercury is relevant to temperature, for example? So to go back to the idea that this is something that can go wrong with the process of doing science, people don't disagree about what even counts as relevant to the theory, then you just can't go through the process of testing theory. It's not certain. You don't even get off the ground. So this should also tell us something about what makes for a good theory. A good theory or good science is explicit about the things that are within its scope of explanation and the things that aren't. If it's not explicit, it leaves this out, where you have something that might be refuting to the theory. You say, well, the construct validity was bad, or my theory wasn't intended to have questions about that anyway. So good theories are explicit about that. The next thing that can go wrong is this next step where you try to find those potentially refuting observations, those observations that might be threatening to your theory. If people don't do that, then theories don't get put at risk of refutation. Again, it's sort of a non-starter. So not only need to define what might be potentially refuting to the theory, you actually have to go out and, or someone has to go out and collect those observations. This idea of like having some sort of systematic way of making sure that theories are put at risk of refutation is enshrined in a lot of norms of science. So there are 4 things that are often called the Mertonian norms. Merton was, I think he was actually a psychologist, but he wrote a lot about like what qualities of the scientific community facilitate good science. And one that's super relevant to this idea, putting things at risk of refutation, is this idea of organized skepticism, or having a structure in place to scrutinize theories. The idea is that part of the process of, or the part of what comes with the territory of being a scientist is having your work questioned. Well, according to this philosophy of science, that's integral to the scientific process. If it doesn't happen, science doesn't get done. This idea is also, if you can find this idea in the motto of the Royal Society. The Royal Society in Britain is one of the oldest scientific societies. Its motto is Nullius in verba, or take no one's word for it. If you want to make a claim, show me the evidence. It's another manifestation of this idea of being skeptical about things in the organized world. So this necessary quality of organized skepticism, that's a statement about how the scientific community should organize itself. It's sort of a prescriptive statement about how science ought to be organized. Another way of thinking about this idea of actually going out and collecting potentially refuting evidence goes back to these graphs that I showed you before. So obviously, if your theory is making a prediction like this, where the only thing that refutes it is a flat line, it's going to be pretty hard to go through that process of actually putting the theory at risk. There's no risk involved in testing a hypothesis with this. There may be not no risk, but very little risk. In contrast, a theory that makes a prediction of, say, a correlation between point 2 and point 3 is at pretty grave risk of refutation whenever someone goes out and applies some observations that might be relevant to the theory. It's at very great risk of refutation. That means it's going to be easier to gather evidence that might contradict the theory. This idea of putting theories at not just a little bit of risk, but a lot of risk is often called severe testing. A severe test is just one that puts a theory at great risk of refutation. So this tells us something about this last category question, which is, how does science progress? Well, one way that science progresses is through critical scrutiny in this process of putting theories at severe risk of refutation. without those ingredients, science doesn't happen. There's no process of theories either gaining this truth-like quality or having to be amended because something about the theory was refuted. The last part of this process, or the last part of this process of doing science that could go wrong, is this last one, which is in the process of actually amending theories. So things are usually okay if you're on the side of the equation if the theory passed the severe test that was put to, because no revision has to happen. You just sort of think the theory is better. Most scientists want to be on that side of the equation. It's often easier. But things are different if you're on this side, where you've got evidence that's contrary to the theory, because you have to actually do something with it. You have to amend the theory, or some sort of process has to happen afterward. So to give you a sense of the kind of thing that might go wrong once the theory is refuted, let's think back to this idea of snakes living on land. If I'm faced with this contrary evidence of green anacondas, which spend most of their time in the Amazon River, I could do two things besides amending my theory that snakes live on land. So one thing I could say is that, I don't trust the photo that you're taking, it's photoshopped. Or I could say, there's something about how you measured living on land that is not good. So I could doubt the validity of that living on land measure. Basically, I could cast doubt on this idea that the observation actually bears on the theory. The second thing I could do is amend the theory, but in a way that is not constructive. So I could say, okay, you got me, anacondas spend all of their time in water, but they're not really snakes anyway. I could say, my definition of snake no longer includes anacondas. So that's a theory where that's a type of amendment that doesn't seem especially helpful. I haven't made my theory better. In some ways I've made it worse because I'm excluding a class of observations that could be relevant to the theory. Anacondas could be really relevant to ideas about snakes, but I've made this amendment to my theory that strategically eliminates any evidence about anacondas. In general, when confronted with contrary evidence, scientists can respond in what I would argue is a less good way most of the time. We'll talk about ways that it gets complicated a bit. So there are two ways of responding that can be not great. So the first is I could doubt something about the observation's validity. I could say you didn't measure, or there's something wrong with your camera. That's not actually water, or the photo was photoshopped, or you didn't look at the anacondas for long enough to know if they really spend most of the time on land. So those are questions about the validity of the observation. So you could think back to those questions about construct validity that I was asking before. That's always one option when you're facing contrary evidence, is to doubt the validity of the constructs in question. Or, more broadly, other stuff that bear on validity. The reason that this is possible is that idea of that observations don't really have much meaning outside of some sort of theory of agreement meaning. That's that idea of the impregnation of observations with theory. So because of that, if you're faced with contrary evidence, you could sort of doubt that those theories that impregnate the observations, so the theories of the measures, not the theory that you're substantively interested in. You could say, yeah, your depression scale, it doesn't pick up on the more active kind of depression that my theory is really about. It only captures a more passive form of depression. And so any studies you do with that measure don't really bear on the theory. The second thing that I showed you was the process of making what are often called ad hoc amendments to theory. The idea is that you modify the theory to sort of strategically exclude the observation in question. You say, well, anacondas aren't real snakes. That's an ad hoc amendment. And the reason that that can be bad is that you're sort of restricting the falsifiability of the theory. It's an open question as to whether this is like really progressing the theory in a good way. The tricky thing about both of these kinds of responses is that sometimes they're the right ones. So sometimes the measure in question really is bad. It has poor validity. And we shouldn't think about certain evidence as bearing on the theory. That can be the right response. And likewise, sometimes it can be good to narrow the scope of the theory because the theory is too general. That can be the right response too. So it's not like these responses are always bad, but they can go badly because it seems clear that they can be used as sort of tools to prevent the theory from being refuted. So I'm not saying that one should never do these things, but they are things that might be a sign that, someone's engaging in some motivated research, or this research line is really in trouble because there's so many ad hoc amendments that make it so that it can only be tested in this very narrow subset of ways. It's not very superior. So I more want you to bear in mind, well, know what these strategies are and how they relate to this idea, this philosophy of science, this way of doing science, and know that they can go badly, although sometimes they are the right sorts of responses. They're not always bad. Tricky thing is knowing when they're bad and when they're not. So we've learned one other thing about scientific progress. Generally, science will progress better if people are making a limited number of ad hoc amendments, a limited number of questions about construct validity, although those things are justified, and actually construct validity in particular is like necessary for any other science to happen. If you don't have theories about measurement, then there's nothing to be relevant to the theory. So, like I said, it's not like these two things are bad, but if people are asking, if a certain scientist is asking too many of these questions or amending their theory, that in too many times in that way, it could be central. So this is a lot of stuff about like what makes for science. One way of thinking about science is this: the person who's most famous for this idea is Popper, Karl Popper. He's the person who focused on this idea of falsifiability. And if you make falsifiability the thing that separates science from non-science, it leads to this process of developing theory that relies on refutation. I'll talk on Wednesday a little bit more about how this applies to psychology and some of the ways of doing statistical tests that we talked about throughout the semester, these ideas do apply. But the thing that's kind of counterintuitive about this way of doing science is that it makes the ability to put a theory at risk of refutation a good thing. It's actually something that you're looking for in scientific theories. It's a thing that separates good theories from bad theories. Often the impulse is to make the theory safe, to make it not wrong, but that's not something that facilitates good science, at least according to this way of doing science. Another important idea is this idea that what even counts as an observation is something that is theory-weighted. So you have to have a theory of measurement about a depression scale to even know if your depression scale is relevant to your theory of depression. And then there's, lastly, there's this idea of critical scrutiny and organized skepticism as being core to helping science progress, because that's the only thing that leads to theories gaining this truth-like quality or having to be amended. And the last idea is this idea of severe tests. So generally, we should prefer tests that put a theory in great danger of being wrong, because those are the tests that are going to be most informative. So I think the philosophy of science is one area where, I like, learning by doing in general. This is one where we had the time for homework on Friday. I would probably put a question like this on Friday. But I wanted to have a little bit of discussion on Wednesday, like, instead of just me talking at you, discussion of theories that are relevant to your area. Thinking about them in terms of falsifiability. So for the next class, you don't have to write a dissertation on this. It doesn't have to be long at all. But I at least want you to find an empirical paper that's relevant to your area that tests the theory. And think about, one, what would count as contrary evidence to this theory? So what evidence would prove the theory wrong? And second, to what extent in the paper are the scientists in question actually putting their theory at risk of refutation? So I mentioned how there are some ways of doing tests that are more or less severe. How severe is the test in question? And for the first part of class, we'll talk about what you find. And then I'll talk more about how these ideas apply specifically to psychology, because that's a lot of what we do here.
Just an email. Or
I made a forum on Blackboard, so you can post the forum. Yeah, problems, let me know, but it should work just fine. That's the two questions at the top. All right. See you on Wednesday.
That's